Okay.
All right, so let's start doing some differential equations. Kind of introduced the idea last time. Let's start getting more specific. We're going to start with chapter 1. We're going to talk about classification of ODEs, and we're going to talk about the three models that we can use ODEs to model. We'll look at more models as time goes on, but basically going to cover chapter 1 all in like one thought. Right? So I think there are like 2 or 3 sections in chapter 1, but I'm just going to keep one story here. So let's actually just jump into it. Equation that involves function and its derivatives is called a differential equation. That's all it means. If we have a single variable function and ordinary derivatives, that is just like derivatives as you would see them in Calc 1 and Calc 2. We call the equation an ordinary differential equation. We abbreviate this for ODE. Now, if there are several independent variables, and partial derivatives occur, it is called a partial differential equation. Create PDE. As I mentioned before, the majority of our time will be spent on the ODEs, but we will do a few partial differential equations towards the end of the course. Here's another definition. The order of a differential equation is the highest derivative that occurs in the equation. Okay, so that being said, so that is just to think of an ODE in more sort of abstract terms or more specific terms, I would say an ODE, an nth order ODE is an equation of the form here's how it's going to look. There is going to be some function of a bunch of variables. T, which is I'm going to use for the independent variable because often our independent variable will be time, though not always, could be x, could be whatever, but t is very typical for a differential equation. Y, which is the dependent variable, this is the function of t. Then you have y prime, y double prime, dot, 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 all the way up to y to the nth derivative. So once the highest derivative that occurs, like the fifth derivative is the highest derivative that you see in the equation, that defines the order of the differential equation. So I can say that's a fifth order differential equation. Equals some constant. Okay, so where t is your independent variable, y is your dependent variable, k is a constant. Okay. So examples, I wrote some down last time. That is a differential equation. That is a differential equation. That is a differential equation. Based on our definitions, these are both second order ODEs. This one is a first order ODE. And notice that I can actually, in order to get this form, I could move the sign t to the other side to get the constant 0 on this side, and I'll just have some function that mixes together the t's, the y's, the y primes, all that sort of good stuff. Okay. So that is what a differential equation is. It's just an equation that has derivatives in it. Once you have a single variable function and only one independent variable, we call it an ODE. If it has multiple independent variables and partial derivatives, we call it a PDE. Yes. Definition. If f above is a linear function, it's a very important class of ODEs. It's a linear function in the dependent variable. It is called a linear ODE. Or if I'm lazy, LODE. Right, so these are a very important category of ODEs, the linear ones. They're very useful for multitude of applications. Let's make sure that we know what these things look for. So I'd like you to, basically these are all ODEs. Classify the following. So basically I want you to tell me the order and tell me whether it is linear or non-linear, would be the opposite of linear. So here, A. So these are all examples of differential equations. Classify them, just to make sure we know what we're looking at. Right, so clearly these are all differential equations. That much should be clear. Why? Because you see derivatives. Now just to make sure that we understand order and linear versus nonlinear. What's the order? So this is first order linear. This one?
Second order.
Second order linear.
Second order nonlinear.
Second order linear or nonlinear? Non-linear. Why?
Because y times y prime.
Because you have the y times the y double prime. This means your y isn't, it's not linear in the y's, right? This one?
First order nonlinear.
Right, so this is first order non-linear. Why? It's the highest order that occurs in the first order, but this y here is squared, that means it's non-linear. What about this one?
First order nonlinear.
Again, first order non-linear. What about this one?
Second order nonlinear.
Second order linear or non-linear?
None of
It's linear. Why is that one linear? Yeah.
the y double prime is not being multiplied by other y.
Right. The y's aren't mixed together. You're not raising a y to a power. Y is not in a trig function. Notice that we have x squares, we have sine x's. These are not linear functions, but we don't care. I care about being linear in the y. The x's can do whatever they want, as long as the y's are behaving like linear functions. So if you imagine all the x's are like constants, this will kind of look like a linear thing, right? A constant times a y, a constant times a y, and a constant times a y. That's linear. Yeah.
I thought we want a constant on the right side of the equation, but 2y is...
I can subtract 2y from both sides and get 0 on the other
Right,
side.
right.
In general, when I define something as an equation, the assumption is I can manipulate it to be in that form. It might not be given to you in that form. This will be something of a general principle. Yeah.
I'm sorry, can you explain again why E is nonlinear?
Because it's sine of y.
Oh,
There's a y plugged into the sine, right? So that one's bouncing up and down. It's not like a straight line. Okay. Now, the classification is super important because the order and whether it's linear or nonlinear is going to determine what methods can and cannot work. So there are certain things that if it's linear, you know, oh, I can try these methods here. If it's nonlinear, they don't apply anymore, right? So you have to first be able to look at what, see a differential equation and talk about its type. And we have a lot of theorems that go with linear ODEs and some that don't. And so it's important to first of all classify them. A lot of our time is going to be spent on the linear ones because most of you are going to need this for engineering, and in the engineering context, when you're doing an ODE, chances are it's going to be linear. But we will spend a little bit of time dealing with the nonlinear.
I have a question.
Yes.
Just to clarify what you mean by something being linear in y, does
Yes.
that mean that if another variable shows up, you treat that variable as some constant?
Yeah, it means if when you're looking at it, you see the dependent variable, just for a second, pretend everyone else is a constant, would it behave like a linear thing? So the y's should not be raised to any powers. You shouldn't have y's multiplying y's. You shouldn't have y's plugged inside of trig functions. It'll be a y thing to the power 1 times a constant. You will only have to have terms that look like that. So that's how you determine it. Any other questions so far?
I have a quick algebra question.
Yes.
Is y double prime divided by y prime equal to y prime?
No.
Okay.
So let us talk about, so now we know what differential equations are, and hopefully in the first lecture I gave you some ideas why it's important for us to deal with them. So now let me specifically tell you how to solve an ODE. So, given this, and you can identify what it is and what its characteristics are, how do you go about actually finding an answer? What does it even mean to find an answer? To solve an ODE. It's like T, Y, Y prime, the n plus k means to find a function y that makes the ODE true. What you need to find a function y that makes this, whatever it is, a true statement. And this may be explicitly or implicitly. So, hopefully you remember from tacos what implicit and explicitly defined function means. This one is preferred. If you can get it to that point, I expect you to get it to that point, but if it's really annoying to get it to that point, I would settle for the implicit case. Explicit means that you have y on one side and all your other variables on the other side. Implicit means they're mixed together and you can't really separate the x's and y's. So it's another state, it's another equation that looks like this. But what you want to notice is that there are no derivatives present.
In both situations.
In either situation, derivatives present. So basically, to solve an ODE, you want to find a relationship between the function and its variable that does not involve any of the derivatives. If you can find such an expression, whether explicitly or implicitly, we say you've solved the differential equation. And what that means basically is, you're going to try to find the function so that when you actually plug it into the equation, it makes sense. So, for example, in C right here, you want to find a function so that if I take its second derivative, multiplied by the original function, plus take 3x times the original function, after I calculate and simplify everything, 7 is going to be the answer. Right? You want to find a function that does this. It makes this equation true. And once you can do that, we say you've solved the differential equation. So I'm going to give you a differential equation. You're going to classify the differential equation in your head. You're going to say, oh, that's a second order linear. I know what to do. You're going to go through some method that I will be teaching you. The end of that method, you should have either a statement like this or a statement like that, from which, if I take that statement and plug it into the original equation I gave you, it will be a true statement.
So there's a process by which we can check.
Oh, there are all sorts of processes. And the check is by you actually plugging it in and seeing if it's true. But to get to that situation in the first place is challenging, to say the least. Or usually. I mean, we'll be doing the easier problems, but so let's actually do a very easy example. Let's take our time, ease into it, so that you can kind of see what I mean. So, example. If I were to tell you solve this differential equation, dy dx equals what?
y squared.
Huh?
Y squared.
What about, like, this is the example I'm giving you.
Eating it.
That's the example.
No, that's if we can do it.
Okay, so,
It would be harder with y squared.
would it though?
That would be easier, actually.
I don't know. What would you say?
Well, could we move?
Can you do that? Can you tell me a function that makes this true? Yeah.
Move dx to the right side, and then dy underneath, do y underneath dy, then take
And can you tell me a function that makes this statement true?
yeah.
E to the x is an example,
Yeah.
right? So for example, you know that y equals e to the x is a solution, right? Why? Because if I take dy dx of this, I get itself. This is a statement that says the derivative of some function with respect to x is the original function. So now you want to think, what does it mean to solve that equation? Well, tell me a function for which that is true. Okay? Y equals e to the x is one solution. Is there another solution?
Y times x.
What constant? 0 is another solution. Any other solutions? Right? If I take the derivative of 0, I get 0. That's getting itself, right? So 0 is also a solution. Anything else? Yeah?
Any constant times e to the x?
Any constant times e to the x. Now we're talking, right? Because if I take 3 times e to the x, differentiate 3 times e to the x, what do you get? You get 3 times e to the x. 5 times e to the x. The derivative is 5 times e to the x. Any constant times e to the x, that derivative is going to be itself. You can also notice that this case covers this 0 situation. Just plug in c equals 0. So I can tell you that this represents all solutions. Now, that is something that has to be justified, I know, but for the moment, just take this on faith, right? So sometimes you're going to wonder, maybe there's some other function I'm not thinking about. Maybe there's another function that's like e to the x that no one told us about in Calc 1 or Calc 2, and that would solve it, but e to the x is the only one I can think of. But no, this is everything, right? Every solution to this thing will be that guy. And at some point, we're going to have a theorem called the existence and uniqueness theorem, which is going to tell us that. Basically, again, I'll talk about it in the future, but basically there's a theorem that says if you have an nth order linear differential equation, it will have n linearly independent solutions. This is a first order linear differential equation, which means it has one type of solution, right? If this was a second derivative, I should be able to find 2 kinds of solutions, and so on and so forth, right? Now, that's an exercise in linear algebra, which is kind of why I want you guys to know about linear algebra a little bit. But that's key. This actually represents all solutions. Now, notice there is one thing you notice here is there's actually an infinite amount of functions that solves this equation. Okay, so a solution like above, where a family of solutions solve a differential equation. Is called, we would call this the general solution. So the ability to tell me like an entire class of functions that will solve this. Anything that looks like a constant times e to the x will solve this equation. I can say you've given me the general solution. This is how you would solve this thing in general. There is an infinite amount of things that will work here, but they all look like that form, right? So this is what it means to solve a differential equation. I was given an equation that looks like that. And what I did was I found an equation that looks like that, such that when I take this and plug it into here, it's true, right? So again, very simple example, but I want you to get the idea before we start doing anything fancy. Any questions about the idea? Now I know it kind of looks like we're just like guessing and checking, but we'll get to a point where you can actually find the solutions here. Now, I mentioned a general solution, which would suggest that there's another kind of solution. And there is. Let me introduce that kind of solution right now. Sometimes a specific member is required. So sometimes not only do you want to find a solution to a differential equation, you want to find a solution that behaves in a particular way. And how you would represent that is by someone telling you about values of the function. So for example, just to kind of tweak this easy example here, what if someone told you, okay, dy dx is equal to y, and, that's a comma, I require that if I plug in 0 into the function, 5 is the result. Now, not every function is going to do that, right? So, this thing here is called an initial condition. That's what it's called. Whenever you see that, it means a general solution is not good enough. You want to find a very specific solution. Now, and this is just another vocabulary thing. An ODE with given initial conditions. You can have multiple. In general, you have to have as many conditions as the order of the differential equation. So chances are to find one particular function for an nth order ODE, you'll need to know the position, what the function is doing at n different points. Or I'll talk about that in a little. With given initial conditions, it is called an initial value problem. So that's an ODE. This is an initial value problem, right? It's an ODE with some given condition that I must fulfill. So now, we've already solved that guy. We know that this is the guy here, right? So now, all we have to do if given an initial condition, so given that y of 0 equals 5, all I have to do is take the family of functions and plug in the point that I was given and kind of solve for the guy, right? So this would mean that if I plug in 0 for the x, the output, the y, will be 5. Of course, e to the 0 is 1, and so this means that c will be equal to 5, and so this means that y equals 5e to the x solves the initial value problem. Right? So I found here an infinite number of functions is represented. I found a specific one, a particular one, that solves this differential equation and at the same time passes through that point. So, not very imaginative here, but people have never been imaginative with naming things. This is a particular solution that works. We call it the particular solution. Not kidding, that's the official name for this kind of solution. This is the kind of thing that solves it in general. What do we call it? General solution. This is something that solves it in particular, the particular solution.
Professor,
Yeah.
when we have something given, for example, if we want to find a spring location or spring position at a certain time, have to put that time into that position? Like for example, okay.
So there will be times when you might be told of some differential equation being satisfied, and I know at this time it's in this position,
Okay,
and it's also moving at this speed, which is someone telling you y prime at a certain value is something. And oh, it's accelerating by this much, that's telling you y double prime at a value is something. And then using all that, you can actually come back and figure out what's going on. So yeah, this can be extended to the further derivatives. but we're starting out slowly.
Okay.
So yeah, ODE, to solve it means I want to find an expression that makes it true, given some initial condition or several initial conditions. If I find a specific guy from the family of functions that make it true, that is called a particular solution.
So you will always be finding the general solution prior to the particular one, right?
You always find the general prior to the particular, because to find the particular, you need to plug into the general. Yeah, so that's always going to be. I don't know how to use these 3 boards. I don't think there's this. I haven't used this in a while. Let's see this. So I'm sure this phrase you've heard before. Where we can just see the answer. We say we solve by inspection. But inspection won't always work. What if we couldn't? What were some alternative ways to deal with a differential equation?
Doing like a vector field or?
So that's chapter 1, where they talk about the direction fields and stuff like that. I'm going to talk about that. But I want to mention first something that you mentioned earlier, which is most people when they're talking about derivatives, including myself, we like to use the prime notation because we're lazy. It's hard to like dy or dx all the time. Just write y prime, move on with your life, right? But the Leibniz notation is super useful. It's actually very functional, and you would have seen this in Calc 1 as well, but you can actually treat it as a fraction a lot of the times. You can separate the dx from the dy, you can multiply both sides by dx or things like that. And so you can actually, the dx and the dy, these are called differentials and so on and so forth. And we know that we can actually manipulate them as if they were like numbers. So here's one alternative. Given dy dx equals y, here's something you could do. I could multiply both sides by dx. And then, assuming y is not 0, I can divide both sides by y. Now, probably at the moment this doesn't really look like it's helpful to you, but look at what happens now. Now that notation looks familiar to me. I kind of know what to do at this point. I can separate the x's and the y's and integrate both sides because I have my dx and my dy. They're like the nice ends of the integral here. And here's where we need calculus. What is the integral of 1 over y? No. ln of absolute value of y. What is the integral of that?
X plus c.
X plus c. Now, technically you have a plus c on this side, but we just, in our mind, we move both c's to that side and there's just one c.
Oh,
right?
okay.
So, you'll have something plus c1, x plus c2, move both of them to one side, call it plus c. Right? Now, at this point, that is actually a solution. That is the implicit solution, right? That is an expression that makes the differential equation true, but it's also an expression that's super easy to just solve for y, so I'm just going to solve for y. So now, if you have an expression like this, how do you solve for y?
E to the power of that.
Well, you plug both into the power of e, because you remember from algebra pre-calc, maybe, that e's and ln's cancel each other. So you plug both sides into the power of e, That's going to cancel this side. You're going to have absolute value of y. Over here, you're going to have e to the x plus c, which doesn't look like what we had before, but it's actually the same thing. Anyone see how it says?
E to the x plus c is the same as e to the x plus c.
Right, this is e to the x times e to the c. Laws of exponents, way back in algebra class. And this thing, I just call it a c, like whatever. Technically, this is a c1 and a c2, and that's a c. I don't care. At the end of the day, it's just a constant. Now, because absolute value of y, I know it can take a positive or a negative sign, I just kind of drop the absolute values because my c can take care of whatever sign I might need. And so ultimately now I end up with y equals c e to the x, which is what we did before. Okay? So there's a method where you could literally compute the answer, right? And this is the kind of processes that I'm going to teach. I'm not going to teach you how to look at something and tell us the answer. I'm going to teach you how to find the answer. Now, while you won't need it here, the questions I'm going to ask in class are a lot harder than that one. So you can get to the solution that way. BTW, this process, which we'll talk about more, is called separation of variables. Again, keeping up the tradition of math people not being able to name things in a creative way because we separated the variables. Right? We put all x's on one side, all y's on the other side. We separated the variables. What do you call it? Separation of variables. This term is fundamental to calculus. What do we call it? Fundamental theorem of calculus. Yeah. This says any continuous function attains all intermediate values. What do you call it? Intermediate value theorem. And then they're like, this allows us to find the slope of a straight line, of a function. What do we call it? Derivative. Put on your glasses and you walk out. I don't know why they decided to not name that slope. They just decided, that's the one time that, you know what, this was pretty cool. It needs a creative name, derivative. Yeah, but otherwise we just name things by what we're doing. Oh, we separate things. Let's call it separation of variables. So that's actually a technique. Separation of variables. Just some examples. Solve a dy dx equals x times y. What kind of function will make that true? B. Y prime equals x e to the x plus y. C. dy equals x squared y squared plus x squared minus 4y squared minus 4 dx. For fun, let's put on the quiz problem. I believe I asked dy dx equals y squared.
Yeah.
That was a bonus. So in general, the quizzes will be kind of like the format that I have here, although it will tend to be shorter usually. I mean, I had a lot of stuff to test you on from Calc 2, but it's going to be the same format. Just fill in the blank, and I'll often have like a bonus section that covers topics that I'm about to teach, kind of as a reward to people who read ahead. You know, so okay, here I'm going to quiz you on what you should know already, and I'll give you a little bonus. If you read ahead, good job. You can try to get this, and that will add to your quiz grade. So these are all ones that we can solve using separation of variables. let's actually get through them together. A, dy dx equals xy. What do you want to do?
Move x to the right side, yeah, to the right side.
Separation of variables.
Yeah.
Right, dx to the right side, then
Y.
y on the other side.
dy over y.
So it would look something like that.
And then
End of the day, right? Multiply by dx, divide by y. Of course, we're pretending that y is not 0.
integrate both sides.
Now you're in a situation where the variables are separated. You can integrate both sides. In terms of this is ln of absolute value of y. Technically, you always drop the absolute values because of that c can give you a different sign. Integral of x.
X squared over 2 plus c.
Now what you would do is you can just
Yep.
plug both sides into the e, and then you have y equals c times e to the x squared over 2. Actually solves that. That's the general solution for this one. B. Y prime equals x e to the x plus y. What do you want to do here?
Y prime is the dy over dx.
Rewrite e to the x plus y as e to the x times e to the y. Divide both sides by e to the y. Multiply both sides by dx.
Integrate.
We can do the right one by parts.
How do you integrate that one?
E to the negative.
Right, write it as e to the negative y and do that rule. Integral of e to the kx is 1 over ke to the kx. Ultimately, you end up with minus e to the minus y here. How do you integrate that?
Set x equal to u.
Right, integration by parts.
Yeah.
U equals x, dv equals your e to the x. You're going to get x e to the x minus e to the x plus c. Okay, day one, hopefully you start to see how integration is important. That's why I asked you all those integrals there. And you're like, well, that's not stereo like the ones you asked on the quiz. Hold your horses, it's lecture 1. Okay, so now what I could do is I could write this as e to the minus y equals e to the x minus x e to the x plus c. How do I solve for y?
Take the ln.
ln on both sides. So again, we remember from pre-calc that ln's cancel exponential. So over here, that becomes minus y. Over here, we have ln of e to the x minus x e to the x plus c. And so ultimately, what solves this is negative ln of e to the x minus x e to the x plus a constant. That's the general solution for this guy.
It's fine for the negative sign to be outside the ln, obviously, right? It just can't be in it. Or it can be in it.
It can, it's just that the actual expression, it
Yeah.
cannot take on negative values. So if you have ln of negative x, the assumption has to be x itself is negative, right? So you can't. I actually wrote these down. Oh, I don't do that. I have it on paper. Weird. Now I lost my pencil.
So the negative ln of dx minus x plus c is the same as ln of y.
dy equals x squared y squared plus x squared minus 4y squared minus 4dx.
Factor out y squared.
Okay. And what would we have?
Well, factor out y squared within a bracket so that we can leave minus 4 alone.
There's also the x
There's
squared.
also the x squared.
Oh, my bad. Sorry. I didn't see it.
Can we distribute the x to each?
You could Just read the dx. How does that help though, to have a bunch of dx? That doesn't separate the variables. It looks cool. It looks cool, but no, it's not going to help.
Can you complete the square?
What do you mean complete the square? How will you complete the square?
Is it inseparable?
Implicit, right?
It's separable.
It is? Okay.
Oh. No, it's easy to do.
How are you going to take the square root? What does it mean to take the square root of y?
Can you factor out y squared of only some of the factors, and then leave the other factors with x's on them?
How does that help? Yeah?
Would you do it by grouping?
By grouping. Again, in pre-calc, we learned that if you want to factor stuff where there are 4 terms, factor by grouping is literally one of the first things you have to think about.
Yeah.
So you factor in pairs.
I forgot what that was called.
Factor by grouping is what it's called. There's a common x squared here. I can factor that out. I would have y squared plus 1. There's a common minus 4 here. I can factor that out. I would again have y squared plus 1. Now, y squared plus 1 is a common term. I can factor that out. I would have y squared plus 1 times x squared minus 4. So I end up with that.
With the y squared plus
Ultimately, you divide both sides by the y squared plus 1. We don't have to worry about its value because that's never 0. And now we integrate both sides. Okay, integral of what? 1 over y squared plus 1.
Wouldn't it be like tan inverse?
Tan inverse. We had something like that on the quiz.
Yeah, I think.
Here's where a tan inverse pops up. Yeah, integral of that is tan inverse of 1. Integral over there, that's just the power rule, so that's x cubed over 3 minus 4x plus c. How do I solve for y? Can I solve? Take tangent. Take the tangent of both sides, because that kills the inverse function. That's the general solution for that one. Let's look at D. Now, this is supposed to look like a joke at this point, right? That was on the quiz. It's like, seriously? Okay, how do you do that one?
With the dx to the right side, y squared is dy.
So 1 over y squared dy equals dx.
And with
Integrate both sides. Integral of this is?
y to the negative 2 power on top, and then you.
It's just y, yeah.
Yeah.
Negative y to negative 1, so it's minus 1 over y. Here you let x plus c.
Yeah, got it.
And so now you'd end up with y equals minus 1 over x plus c. That is the general solution there.
Was it a lot of bonus points? Was it a lot of bonus points?
All things are equally weighted, so I just give you 1 point for every correct answer. Which is another thing. So don't, on the quizzes, don't spend your time getting stuck on what, just move through, do everything. They're all worth the same. So you don't want to miss points. We'll stop there. We'll talk about another way that chapter 1 tells us how to solve a differential equation, the direction fields idea. And then we'll talk about a model and then move on to chapter 2. By the way, I see you guys tomorrow. Right? Tomorrow is a Monday schedule. So. I'll also post a copy of the quiz and the answers on the website.
Okay.